Okay, so quick reminder, quick review of what we had been talking about before break. By the way, I hope everybody had a good break. Welcome back. Good to see everybody. We were talking about surface integrals, and the big idea of surface integrals is that we want to look at quantities that accumulate over surfaces, where the whole is the sum of the parts on surfaces. So we write down a new, it's still a chop it up, add it up expression. It's basically the same as every other Riemann sum we've ever written down. It's just, different specifics, different geometric circumstance we're in. We denote this as a scalar surface integral. We draw some pictures and work out some details as to how to actually turn the crank on this, right? And then see various examples where, for example, here we've computed the mass and the moment of inertia and coordinates of the center of mass, etc. They're all scalar surface integrals. Okay. We then tried to apply these same ideas to another computation that happens on surfaces, namely how to compute flux of a vector field. And what we found is that something was very significantly different. For one thing, I need to know which direction you consider to be the positive direction through the surface. You can't just say how much fluid is flowing because different directions are negatives of each other. Which one do you want to call the positive one? Right? So this means we are no longer talking about just a surface. We have to talk about an oriented surface. There is no such idea if you're talking about mass. Mass, just mass. It just sits there. There is no kind of direction of it, right? So that means that we're having to form a significantly different construction. The unit normal being the sort of the new player involved, and thinking as we were about flow rates of fluids through a surface. We ended up writing down all of this stuff, finalizing with our what we call a vector surface integral, so named again for the, I'm going to say obvious reason that, well, of course, our integrand is a vector, and likewise our differential here also a vector. Okay, so we wrote down some equations for how to compute this. A lot of the work had already been done. We had already laid a bunch of groundwork on, how to relate surfaces to parameterizations and pulling back. Turns out everything we needed we already had. That was a lucky break. And we ended up then with a little asterisk, we ended up with a formula for how to pull back a flux through a parameterization. Okay, with that done, we had to think about orientations. And this is a subtlety. Again, there is no version of this if you're talking about scalar surface integrals, because there are no orientations. And we didn't even really notice the kind of analogous situation that comes up with vector line integrals, because if you think about it, with vector line integrals, you're talking about a curve. You parameterize the curve, and when you do, you can kind of almost see the direction that you're parameterizing the curve. You can see which way you're going. Worst case, you take the derivative and see which direction the velocity is pointing. You can totally see which way you're going when you parameterize a curve. It's just not that simple with surfaces. So our new sort of unfortunate, awkward scenario is, while our surface could be parameterized either of two different ways, right? So, how the surface comes to it. What is designated as the positive direction through the surface? Our parameterization kind of ignores that. Our parameterization just kind of arbitrarily picks a unit normal. And they're completely independent, completely disconnected, right? When you make up your parameterization, you're not thinking about the orientation at all. Even if you were, you wouldn't know how to parameterize it the right way. It's just really not clear. So what we have to do then is, after we get to a certain point, once we can see which direction our parameterization is kind of implying, that our parameterization is oriented, we then have to compare the orientation that we inadvertently parameterized, and then compare that with, is that the same as the parameterization, the orientation I was supposed to and it's a coin flip. Okay. All right, so this issue is the plus minus question mark that you're going to find in various places as we go through the rest of this section. Keep in mind, again, the ds vector is part of the given. This is oriented in the direction that the statement of the question says it is. Compute the flux in such and such direction through a given surface. That's oriented as given, whereas the capital N vector, this is oriented per your parameterization. Not a given, that's your choice. And again, you have to make sure that those are the same. Okay, so as we saw last time, if you get it wrong, all you do is you throw in a minus sign. No big. Easy example. Here, you'll notice, again, we were supposed to parameterize downward. That's right in the statement of the question. But when I made my parameterization, I didn't realize as I was doing it, but the moment that I wrote that down, I was already doomed to have gotten it wrong. And that fact didn't reveal itself until we compute the capital N vector and see that, this is not downward, right? So, oh well, right? So the easy solution, again, no big deal. You just observe the oops. And then I missed my, here we go. And then put a minus sign in to fix it. You're all good. That's the beautiful thing about it. Parameterizing it upside down, backwards, however you want to say it, is easily resolved. Everybody on board? Okay, so now I do want to remind you one other thing, and that is it really does matter where you put in the minus sign. A lot of people don't worry enough about this sort of thing, but keep in mind your ds vector, that is oriented as indicated in the statement of the question. Right? The n vector, that's the one that is oriented per your parameterization. It has never heard of the statement of the question. So if there is an incompatibility, then here is where that minus sign has to go, right? And you can't add it on at the end later, and you can't put it at the very beginning or something. So it's important that the minus sign be where it's supposed to be. Otherwise, you have two sign errors, right? And again, in terms of the final answer, two sign errors cancel, but in terms of the argument, two sign errors is two sign errors. Okay. All righty. So with all that said, I think this is about where we left off. We're going to pick up from there. There is a problem of language as to how to talk about these kinds of things. For example, if I look at this surface right here, this kind of bowl-like surface, there are two orientations that I could pick. I can talk about this orientation here. Keep in mind an orientation is a collection of unit normal vectors indicating what we call the positive direction through the surface. So that one I might reasonably call upward. And then there's the other possible orientation. This one, another consistent choice of normal vectors, unit normal vectors through the surface, I might reasonably call downward. Now let me complain about this language a little bit. These green vectors here that I have labeled upward, they're not all pointing directly upward. Well, the thing is, I don't think there is a single word that I could possibly choose that would precisely exactly describe the direction that these green vectors are all pointing. They're all pointing in different directions. I'd need equations and stuff to be able to do that, right? Likewise with the blue vectors that I'm describing as downward. So the point here is to change your perspective on what the goal of the language is. The goal of the language, when you're distinguishing orientations from each other, is not to be precise. The goal of the language is to be unambiguous. Just to distinguish between these two cases. And what I like about this first example is, you look at these green vectors, they're not pointing exactly upward. but they are all pointing at least somewhat upward, and even more importantly, none of the blue vectors are pointing even slightly in any sense upward. So even though, again, this word upward, not precise, but it's very unambiguous. There's no way that anyone could look at this word upward and be, confused as to which one of these orientations we're talking about. Does that make sense to everybody? Likewise, downward. The blue is all the blue, none of the green. Point somewhat downward. Okay. All right. So now, don't make the mistake of thinking that you can just kind of tie yourself to these two words right here and always use upward and downward. You take a different surface, you have a totally different problem. So, for example, looking at this sphere here, well, again, there's two possible orientations. Here's the one that I have here in blue. And then there's this one we have here in green. And notice these green vectors, some of them point upward, but not all of them. Likewise, the blue vectors, some of them point upward, but not all of them, right? So if I were to say upward, which of these, green versus blue, which one of these would I call upward? It doesn't make any sense. Upward is very ambiguous, right? So it doesn't do the job. These words right here, useless to describe this scenario, these two orientations. But I think pretty clear that all these green vectors are pointing inward, right? And the blue vectors all pointing outward. So the point is, you always have to tailor your language for the geometric scenario that you face with the goal in mind of being unambiguous. Forget about precision. We don't need precision. We have equations for that. That'll come as needed, right? But we just need unambiguous. All right. Is everybody happy? Okay. All righty. Yeah. Be on the lookout for good luck. You get lucky sometimes. Capitalize. Take advantage, right? I mean, there are plenty of situations where a problem could be unreasonably intractable if you brute force it. But a couple of key observations, and it's a snap. So very important to be on the lookout. Again, I benefited dramatically from this kind of thing when I was an undergrad. The physical world is full of geometric good fortune. So, example, here's a surface. We've got the surface rho equals 3. That's this surface right here. We have a vector field there. I want to compute the flux through that oh, God, I got that backwards. The flux of that vector field through that sphere. How would we compute this flux? Okay, now again, you can parameterize and plug and chug. Let's think that through for a second. If you parameterize, you could use the spherical graph parameterization. Sines and cosines all over the place. That means that each one of these is going to have sines and cosines all over the place. That means that your partial derivatives are going to have sines and cosines all over the place. That means that your capital N vector is going to be chock full of sines and cosines. This is going to be a sine and cosine nightmare, right? That's not to say it's not doable, but the point is that's a slog, right? We don't really want to have to do that. Okay, so what I'm going to do instead, before I resign myself to plugging and chugging, let's see what we can come up with geometrically. And real neat fact about spheres, you got to love spheres. When you have a sphere, specifically a sphere centered at the origin, the normal vector is always parallel to the position vector. I think we talked about this in a previous example before Thanksgiving. Neat fact, unique to spheres. Spheres centered at the origin, to be more detailed. Once you make that observation, it's actually pretty straightforward to find a formula for your normal vector just position vector and find the unit vector that points in the direction of that position vector. So x over 3 in this case, because the radius is 3. So I instantly know what my unit normal vector is. No parameterization, no partials, no cross product, capital N, all that business. I don't need to. I can just write that down. The vector field, of course, I still have, and so that vector field I can rewrite like so. And lucky break, as it turns out in this case, this dot product is 0, and we are done. Right? I didn't have to parameterize it. Everybody see how that works? Kind of beautiful. So now I will point out, you won't always get this lucky, even if you have a sphere. I mean, sometimes, often even, the dot product won't be 0. But it still might be a constant. If it turns out to be a constant, then you can just say, oh, okay, well, I'll multiply the area of the sphere by that constant. Or it might be easier to deal with than the parameterization would have been in some way or another. And of course, it might not be. You might still have to parameterize. The whole thing might still require all the full slog. That's still a possibility, of course. But it's definitely worth keeping your eyes open, head on a swivel, looking for these potentially awesome bits of good fortune. How are we doing? Does that make sense to everybody? Anybody comfortable with any of this? Okay. All right. Here's another one. Now, this is a different kind of awesome luck. Let's see here. Why don't I do this here? That gives me more space to work with. Different surface here. Bunch of discussion there about what this surface is. I'm not happy about this inequality here that has quartics in it. That's not encouraging. I don't like quartics. But anyway, that's our surface, and then we have a vector field here, which is very inconvenient looking, and so this looks like it's going to be another really hard one. There's a lot of potential for this to be outrageous. Think about the bounds that we would end up with if we had to do this as a double, pull it back to ds dt. This is going to be ugly, right? Okay. So here's the beautiful observation. Ugly though that surface is, it's all contained within this plane. And if y is equal to 3 on my entire surface, y squared minus 9 is 0. And that applies over my entire surface. And if it applies over my entire surface, I can go ahead and write that down. For this entire calculation, with y being 3, my entire second coordinate just 0. It's a neat observation to include in there. A bunch of ugly just disappeared. Right? Already happy. Here's the other thing I can capitalize on. This is just a different cool observation. Being as our surface is in this plane, I can just immediately write down the normal vector. It's 0, 1, 0. I mean, that plane is perpendicular to the y-axis. There's only two possibilities. It says right here I'm oriented in the positive y direction, so it's 0, 1, 0 instead of 0, negative 1, 0. So write that down. Right? That goes here. And game over, because, again, no parameterization. Don't have to parameterize at all. Independent of how that might work out, the dot product is clearly 0. We're done. Problem solved. How you like it? Everybody okay with that one? Does that all make sense? So very important. Again, keep your head on a swivel. Always be on the lookout for this kind of thing. You don't want to, every single time you see a question, just go straight to that plug and chug algorithm, because that can get out of hand. That can be rough. It might even be intractable. And just as a strategic observation, I would never do that to you. Right? I would never make a question for the exam where you gotta parameterize and slog through 5 pages of algebra right there on the exam. I would never. I have no incentive to do that. right? So if you look at the question and it looks like there's, oh my gosh, this is going to be outrageous. Like you look at this, come on, there's no way, right? Strategically, you can kind of think, I wonder if because of that, that might mean that there should be some sort of cool symmetry or geometric good fortune or something that simplifies the question. So, yeah. All right. Okie dokie. So here's another one of these weird things. I want to remind you that we talked about coordinate line integrals. Coordinate line integrals were sort of a result of a notational observation that gave us sort of a notational alternative for how to represent vector line integrals. And we didn't really like it, but it's there, and we have to be aware of it because it's out there, and you're going to see it in different contexts. So same deal here. It's just a matter of kind of writing things down and observing what the notational alternative ends up being. So here we go. Our old formula for the ds vector. Always remember that your ds vector comes from the orientation of the surface. Your capital N vector is oriented from your parameterization. It's maybe not in terms of them pointing the same direction. So that you always have to think about whether there's a plus or a minus there, and that's so I put that there just as an acknowledgement of that fact, and I'm not going to talk about it more than that. But that said, you can take your N vector, which is that cross product, just write it in coordinates. Take that cross product, write it in coordinates. I haven't really done anything. I'm just cranking it out. And the weird thing to notice is that as you do the cross product of these two vectors, each of the coordinates is, this times that minus that times that, because that's how cross products work. And as it turns out, each one of those coordinates is a 2x2 Jacobian determinant. As it turns out, now again, this is an easy little bit of algebra here, and strongly encourage, multiply this out, write down these expressions, notice that they are these Jacobian determinants. And before I go on, I want to point out this is surprising. After all, why should we see a two-dimensional change of variables thing when we're not doing a two-dimensional change of variables? We're looking at a surface in space. This is three-dimensional, not two-dimensional. What's with the two-dimensional? Right? Now, if anyone's curious, turns out an excellent reason that leads to some natural geometric observations. It's very cool. If you're curious, it's a 15-minute conversation. Come to my office hours. I'll be very happy to discuss. Sadly, that's 15 minutes we don't have in this class, and it's not essential, so I'm not going to talk about it here. But if you're curious, please come talk to me. I'll be happy to explain. I'm going to just take what we've got here. Let's see here. Take this, distribute the ds dt, and ask now, what should we call these coordinates? What should, for example, looking at this thing right here, what should we call that third coordinate there? And flashing back to chapter 5, again, when we were doing change of variables, partial xy, partial st times ds dt, we've seen exactly this many a time, right? I mean, lots and lots. And the cringy, nonsensical, but satisfying little cancellation suggests that we really ought to call this dx dy. And again, this is nonsense, but there is no cancellation. That's all just kind of convenient, notational luck that I'm capitalizing on. But I think this is a reasonable thing to call it dx dy. With that in mind, everybody buy it? It's just notation, yeah.
So do you remember back? I forget exactly what we were doing, but it would end up being I think it was chain rule where it would be like ds to dx times dx dt, and you made the distinction that we can't just cancel the dx's.
Yeah, I know.
But like here we can. Why is it that we can't here?
It's don't think of it as that the notation is the answer to that question.
Okay.
The notation is the illusion. That's the veneer that we put on top of the truth. Okay. Right? So the reason that it doesn't work when you're doing the chain rules, because of the chain rule, and the notation just gives you the wrong answer.
Okay.
Or I'll say the hopeful notational nonsense happens to be wrong there. Here, the hopeful notational nonsense, and I emphasize this is nonsense. Okay. This nonsense, coincidentally, happens to give you the right answer. What are the odds? Every so often you get lucky. Right? But so don't focus on the notation. The notation is the distraction. The truth of the matter is what decides if it's right or wrong. Is that satisfying?
Yeah.
Okay. How about the rest of us? Everybody good? Okay, good question. So, likewise for these other things, and check it out. We have ourselves a new alternative notation for our ds vector. And with that in mind, here we go. ds vector is now dy dz, dz dx, dx dy. Our vector field, whatever we're taking the flux of, we need some names for its coordinates. It's actually pretty standard to call them PQR, no particular reason. It's kind of a weird choice, I think, really, but anyway, pretty standard. And then you can crank out this dot product, right? This dot product just straight turns into this. No tricky curves on that one, right? And son of a gun, look what we've got here. Our vector surface integral can alternatively be written like this. This is what I'm going to call a coordinate surface integral, right? Still a surface integral. Notice this is still adding up over the surface, whatever surface you were doing the flux through. But weirdly, the differentials are not surface area or the ds vector, surface differential. Now the differentials are dy dz, which makes it look like it's in the yz plane, but it's not. It's on the surface. And dz dx and dx dy. So it's one of these weird-looking critters. It's very, I'm going to say, unintuitive. And I think at a glance, certainly. I am a much bigger fan, it's certainly in the Math219 context, of our older notation, because the vector field's a natural thing. It represents our fluid flow, or our forces, or whatever, intrinsic to the question that came up. ds is a natural thing. It describes a little piece of surface and how it's oriented and what its size is. These things mean something relatable. And this down here, a lot more opaque and clunky. Look how big it is. Right? Why would I ever want to do this? Reasonable question. Right? All right. Well, so it turns out there's some good reasons. They don't really apply in Math219 very much. But this kind of notation, this is what differential forms look like as it turns. Integrals of differential forms look like this. And that's important because integrals of differential forms are super powerful. Extremely good. I mean, you can prove theorems with them that eluded the great 19th century mathematicians. And so really, really natural in these powerful ways. So as a result of that, a lot of people love this notation. And because they love this notation, it's in common use, which means it's in your future. Whether it should or shouldn't be, right? You're going to see stuff like this. And so because you're going to see it, you need to know how to deal with it. And here's my advice. Whenever you see this notation, just in your mind, translate back to this notation. This is what I do. Right? Anytime I see something in coordinate surface integral notation, I think to myself, okay, look. This business here is just code for the ds vector. Those are the coordinates of the ds vector. And so what this question seems to be about is apparently PQR is my vector field of which I want to compute the flux. That's it. for our purposes, I think that's the best way to approach when you see something like this. Everybody all right with that? Okay. Symmetry theorems. Good news. It's just like with line integrals. Scalar surface integrals too have a symmetry theorem, specifically an odd symmetry theorem, with the same morally equivalent conditions, same result, same asterisks. You need both conditions to hold. Same plane of symmetry for both the integrand and the domain. It's just like every other symmetry theorem, every other odd symmetry theorem that we've seen. So I'm going to call this just purely good news. It's exactly what you would hope. And I'll remind you, big fan, right? I encourage you to use odd symmetry theorems when they come up, because it saves a bunch of trouble. Again, warning, they are delicate. They are landmines because if you try to apply symmetry, but one of these conditions doesn't work, right? Or something goes wrong, right? Then everything you've written down is toward an argument that fails. It's not actual progress toward an actual solution. So again, that's the big risk. You have to be really, really careful if you use a symmetry theorem, but nevertheless, really worth it. Okay, yeah.
In this case, is P the surface?
No, P is the plane of symmetry of the surface. Yeah. So you've got some actual domain that's going to be, whatever, some symmetric surface, and then P is the plane through which it is its own reflection. Yeah. Everybody good? Okay. All right. Now, just like with line integrals, this is scalar only. Scalar surface integrals only. Very important. It just only works for scalar surface integrals. Here's how it plays out for vector surface integrals. If you're going to have a vector surface integral like so, if you were going to have an odd symmetry theorem, if you wanted to be able to benefit off of your vector field being odd, what you would need for that to work would be for the ds vectors to be the same on either side of the reflection. I would need for ds for this piece and ds for that piece, I would need those to be the same. And here's the problem. While the ds scalars are the same, right, these two little pieces of area, I can slice it in such a way so that these are literally the same areas. These normal vectors aren't, right? The normal vector, the little n, they're just not the same. So it's just flat. Doesn't work. Crash and burn. There is no odd symmetry theorem for vector surface integrals. So do be careful with that. Please don't try to use an odd symmetry theorem on a vector surface integral. Makes no sense. So, and to be clear here then, big X there. Yeah. Everybody clear on that warning? Okay, I think this is the last thing I want to say about 7.2 before we go on to 7.3. This is my own little personal thing I think is really useful to note for a couple of reasons. I'll get to the reasons after. It turns out, unexpectedly, that vector line integrals and vector surface integrals, even though they come from completely different physical applications, have a tremendous amount in common. It's most people wouldn't just notice it at a glance. But now let's think through where do these things come from. Vector line integrals, think about our motivating example of vector line integrals was work. Okay. Vector surface integrals, our motivating example was flux. Completely different physical quantity. Totally different scenario. There's no work involved in flux. There is no fluid flow involved in work. They're just totally different things, right? So, and yet, I claim that these are both special cases of the same construction. These are both examples of integrals of differential forms. And again, I'm not going to tell you what that is, but even if I don't tell you what it is, simply knowing that they are special cases of the same elusive, mysterious thing will make it believable, I hope, that they should have a lot in common. After all, they are the same thing deep down. So I want to show you all the things that they have in common. These are the kind of the giveaways that these are the same thing. So I have a little summary page here where on the left side of the line I have a bunch of old established facts about vector line integral. All this is vector line integral construction stuff on the left. All the stuff on the right of the line, this is vector surface integral stuff. And let me just kind of walk through kind of back and forth between the two. And here we go. I parameterize a curve. I parameterize a surface. Apologies, by the way, for how this is drawn. I just horizontally, I ran out of space. I don't have enough width to be able to draw these parameterizations going straight over, so I had to kind of sneak the target underneath. It looks a little weird, but that's just because of the shape of the paper. Nothing more. Sorry about that. Okay, so parameterizations, for each of which I can take what I'm going to call a derivative. The velocity is the derivative of the parameterization x. And I'm going to say that capital N is a derivative. This is a derivative of sorts of our surface parameterization x. And you might think, well, that doesn't sound familiar. But if you think to the formula of what capital N is, it's a cross product of the partial derivatives of your parameterization. So it literally comes out of derivatives. Okay, now, where does velocity show up in these equations? Where does capital N show up in these equations? And what you're going to notice is that they show up in analogous places. Right? And I've deliberately laid them out on the page so that they will be visually analogous locations. All right, let's see here next. Let's talk about the orientations. When we have an orientation on a curve, that is a unit tangent vector. When I have an orientation on a surface, that is a unit normal vector. They are different, geometrically different. Lots of things are geometrically different in this analogy. This is a curve, this is a surface, one-dimensional, two-dimensional. Of course, there's differences, right? But notice where that shows up in the equations. Totally analogous. Let's talk about the sizes. The ds scalar here describing the length of that little piece of curve, and then the ds scalar that describes the area of that little piece of surface. Well, again, geometrically different, but both represent size appropriate to the context. Both show up, again, in exactly analogous places. It's starting to look suspicious, I think. You know, such a strong analogy. Here's the next one. Let's look at the dx vector. The dx vector here. This is the vector that tells us, as I like to say, everything I need to know about this little piece of curve. By virtue of its direction, it tells me the orientation. By virtue of its magnitude, it tells me the size. Over here on the surface side, we have the ds vector, which again tells me everything I could want to know about that piece of surface. By virtue of its direction, it tells me the orientation. By virtue of its magnitude, it tells me the size. In this case, the area. And again, they lay out on the page in these equations in exactly the same way. Right, last one I'll throw in here just for completeness, I guess. You can look at the dt representing the size of that pullback interval, ds dt representing the area of this little pullback subrectangle. both representing size and the pullback, both showing up in the same places in the equations. So I like the way the color coding emphasizes the strength of the analogy here. It's bonkers. It's perfect. It's incredible how much analogy there is between those equations and these equations that are, geometrically they're totally different. Of course they are. But the analogy is super strong. Okay, now, by the way, this continues. I'm going to let y'all fill in the blanks on, if I can get this thing to, come on, man, there we go. Okay. Let y'all fill in the blanks on the rest of, the color coding down here. But all of the different ways that we wrote work integrals, all the different ways we wrote flux integrals, and you can, go line by line. And again, the color coding is exactly analogous. Oh, okay, so why do you need to know? I'm going to give you two answers to that question. One is cultural point. Not everything about math is, how do I compute this? Right? Sometimes it's good to know fundamental truths, deep facts that you might not know all the specific details of. And so, in a situation where I can't show you all the specific details, at least I can give you a glimpse of deeper truths, right? And that's a good thing. So there is a deep truth that is showing its head here. And the deep truth is that vector line integrals and vector surface integrals, they're very different physical manifestations, but they are mathematically kind of the same thing, and you can really see how they might be the same by the strength of this comparison. Right? Okay, so that's the first reason. The second reason is a little bit more, quite a bit more practical. Just simple matter of, as you are learning this material, it's useful to know that certain things play roles kind of like certain other things. So, for example, a lot of students get confused about the capital N vector. What's the deal with capital N? What do I do with it? What does it relate to? Why do I need it? And I think it's really helpful to be able to think to yourself, okay, capital N, apparently that's kind of playing a role kind of like the velocity vector. The thing that points in the direction of my orientation. The thing whose magnitude gives me the stretching factor that lets me compute the size from the pullback differential. Everything that I just said pointing to velocity, thinking about what I already understand about the velocity vector, all of those words apply just as well to capital N. Right? So, to whatever extent you feel like you understand velocity and how velocity relates to vector line integrals, that's a hint. You can hint yourself in trying to make sense out of how capital N is used in vector surface integrals. So I think there's a lot of potential sort of, helping yourself think things through by noting these analogies. All right. Any other questions about this stuff? All right, so we move along. 7.3. This is our last monster section. You may recall section 5.5 was huge. It should have been 3 book sections, arguably. I think 7.3 also should be at least 3 book sections. But the author likes to have them all together, and ultimately it doesn't matter, I suppose. But anyway, just in case you're wondering, it's going to take us at least this full week, and I think Monday of next week is kind of unavoidable to get through all of this section. All right, so that said, 2 big theorems. Stokes' theorem and Gauss's theorem. We're going to take them one at a time. The book starts with Stokes' theorem for reasons that do make sense. But that said, that's a pretty unusual choice. I'm going to start with Gauss's theorem for what I consider to be even better reasons. Pros and cons. By the way, most books are on my side on this. Starting with Gauss's theorem. Now, a thing to keep in mind as we go through Gauss's theorem, motivating Gauss's theorem, it's just like Green's theorem. shameless ripoff, right? It's, the big idea of what we're going to do here is we're going to take all of the fundamental deep down ideas and structures that makes Green's theorem work, and we're going to say, okay, how would I have to tweak that? What's the analogous sort of analogous version in a three-dimensional context on surfaces? And then we're going to just do that, and a theorem's going to fall in our lap. A lot of math happens this way, by the way, where you take a problem with a solution, you look at a different problem, but you see how it's kind of connected to a problem that's already been solved, and then you copycat the solution, and it sometimes just works. Okay. All right. So, first thing we did when we were doing Green's theorem, we had to make sense out of this word boundary. What do I mean by the boundary surface of a solid? All right. So, the first thing, if you have a solid, and here's my solid three-dimensional region here, and this is supposed to be kind of, again, it's supposed to be three-dimensional. Use your imagination. It's hard to draw three-dimensionally, of course, on a two-dimensional screen. But this is kind of like a big lump, and it has an air bubble on the inside. That's what I was trying to draw. Okay, what is the boundary of this thing? First observation I'll make is that there's actually kind of two chunks of your boundary. There's what you might call the outer chunk of the boundary, and here's what you might call the inner chunk of the boundary. Right? This is all a single thing called the boundary, even though it comes in two pieces. Okay. The other big point, and again, you're going to remember this from Green's theorem, the word boundary is now a loaded word. Boundary does not mean, in this case, just a surface. Boundary means a surface with a very particular orientation. This particular choice of orientation is standard convention. It is arbitrary. When it was first done, it was pulled out of thin air. There is no magic inner meaning to this choice. But it has been the standard for 150 years or thereabouts, and so we're definitely stuck with it. And so this is arbitrary, but required by circumstance. So here's the rule. The rule is that the orientation is always away from the solid. So for example, looking at the outer chunk of the boundary, away from here's the solid in green, away from the solid points outward. Now, a lot of people mistakenly think that the convention is that you always orient outward. This is not true. After all, away from the solid on the inner chunk, again, here's the solid. Away from the solid would be that way. That's not outward, that's inward. Right? So be very careful with oversimplifying. Just like with Green's theorem, there's this temptation to say, it's always counterclockwise. Not really. Maybe usually in simple scenarios, I guess, right? But the rule is always such that the region is on your left, right? There is this particular way to actually do it. Here, again, got to be careful. It's always away from the solid. Yes, that is usually outward, but not always. All right. Nobody's shocked, I assume, that we're going to talk about accumulation. Again, this is the big feature that holds everything together for so much of this course. All integrals are in some sense about accumulating quantities. This is a theorem about integrals that we're going to be developing. There is an accumulating quantity on the board, and that's boundary flux. It's an accumulating quantity. To be more specific, boundary flux accumulates over solids. So, by which I mean, if you look at a whole solid, and there's a whole solid, you can talk about, for example, what's the outward oriented boundary flux on that whole solid. Then you could talk about on this chunk called R1, you could, on this green region here, you could talk about what is the outward-oriented boundary flux there, and you could talk about what is the outward-oriented boundary flux there, and the question is going to be, is green plus blue equal to yellow? In other words, is the green boundary flux plus the blue boundary flux, does that equal to the yellow boundary flux? And this is a matter for Wednesday because we are out of time. So we will pick up with this on Wednesday. See y'all later. Welcome back. Good to see you.